hundredth of a billionth of a billionth of a billionth of a centimeter. At that point, the three non-gravitational force strengths appear to become equal. Because remember, once again, the quantum fluctuations have been messing with the strengths. So if you account for the quantum fluctuations and you correct for those messingnesses, like something is messing with your strength. But say if you correct for all of that, then you find that they are actually, wow, they're actually equal. Although far removed from the realm of common experience, because this is too small of a scale for us, you and I don't live in 10 to the minus 29, right? Meters. We don't live in such small lengths. So we think of electromagnetic force as very different from strong nuclear force, as very different from weak nuclear force. In fact, strong nuclear force and weak nuclear force were not discovered as quickly because of that, because we don't play at those scales. We don't encounter those scales. So that's why those forces were also discovered later. I mean, the proton was discovered later, the neutron was discovered even later, things like that. The small things and the small scales are not our scales. I added you on Facebook. Thank you. So, although far removed from the realm of common experience, the high energy necessary to be sensitive to such small distances was characteristic of the roiling, hot, early universe when it was about a thousandth of a trillionth of a trillionth of a trillionth. So that is 10 to the minus 39, so even smaller, of a second old, when its temperature was on the order of 10 to the 28 Kelvin mentioned earlier. So even though these small scales and big temperatures and big energies may seem kind of weird to us because we are obviously here now and the universe looks very different, but actually when the universe first got started, it wasn't so crazy then. As we have mentioned in some of our lives on cosmology and the Big Bang nucleosynthesis and the Big Bang environment, the universe was extremely hot, dense, crazy, and energetic when it got started. Photons were the king of the jungle back then. It was a very radiation-dominated universe. And things were just extremely crazy and hot. And of course, the universe also expanded, so it was also at a different scale back then. In somewhat the same way that a collection of disparate ingredients, pieces of metal, wood, rocks, minerals, and so on, all melt together and become a uniform, homogeneous plasma when heated to sufficiently high temperature, these theoretical works suggested that the strong, weak, and electromagnetic forces all merge into one grand force at such immense temperatures. So what may seem crazy to us now, like, oh, those three forces, electromagnetic, strong, and weak nuclear forces are the same, or yeah, did I say electromagnetic, strong, and weak nuclear forces are the same at that weird small length scale, although that's weird to us now. But when the universe got started, those scales and those high temperatures and energies, just like making everything mixed up in one big molten hot soup of craziness, it wasn't so crazy back then. Okay, so they were basically the same thing back then. And then they just kind of became different things as the universe evolved. Okay, which is very interesting. So very interesting. Although we do not have the technology to probe such minute distance scales or to produce such scorching temperatures. So, I mean, don't ask us to probe such minute scales now or to make the temperature quite so hot now, maybe in Texas, but we can't get the temperatures to be as high as they were when the universe was just getting started. So, but there was a time when the temperatures were so high and the scales were so small that the strong nuclear force, the weak nuclear force, and the electromagnetic